ultimately. It's like our setup is we have like our sink and then like cabinets or cupboard and right next to the fridge. And then typically it'll be like our stove and the fridge space.
Hey Charles, how's it going? I hope not literally. Are you staying cool? Oh, I know. It's been so hot.
It ended shitty. My started peeing. So we had to take the cafeteria and we spent 6 hours. He just has
No, I haven't.
That and then tomorrow I have to fly to Phoenix, Arizona for the day.
To take measurements, the work, yeah, take measurements of the job site.
Fly back the same day so I can make my Thursday classes. And it's gonna be like 110 on that.
That's right. Dude, about the heater bill and things.
Well, my parents are in the hot was it? Where they live.
116. What?
Right now, it's 520. I still have theirs right now, like 113. You know that. It hit 116 on the hard. Next year, I don't think I'm gonna be 110 where I'm gonna be at tomorrow. Oops. Ridiculous.
Hey, so you go against no, you get forced to that.
Yeah, and I have to, since it's just a day trip, I have to go early to prepare for it.
Just gonna hop on 5
I don't make good money.
Estimated for companies demolition company.
Yeah.
That's exactly what I do. I go to the job site, take measurements, double check my blueprints.
Yeah.
And then basically like, oh, this should be this is the job. You're all they're flying on places like oh, this place I've been around, it's like San Diego.
And I just started. And I was kind of hoping like not to have to do this shit already. Like,
Yeah, exactly. Like,
less in minutes this time, it's like, bro. Or in like 2 months. I don't know exactly. And I'm not trying to do one day. I'm just having this like, it's fine. I will let.
oh, yeah, whenever I don't have like. Or I don't have. Still need these guys are really
Murphy's Law? Yep. What's up?
something that you want to do.
Are you sure? Because when we try to save the file,
Yeah.
we should go to the
Yeah. Yeah.
and I'm not sure if it's the same thing with 2021 and 20.
I've been meaning to look into that issue because I think everyone's been having some issues with that.
Oh, yeah.
So I need to look into that a bit more. I just haven't had a chance.
I did what you told us. I clicked on the archive.
Yeah.
And they said that you have to save it.
Right.
So we have to click save. And then when we click save, and it's in the file, there are 3 different files.
Yes. Yeah. So I think everyone's been having issues with moving forward. So I need to look into that a bit. And then, once I have something, I'll look at it. Yeah.
Mechanical, but he went to.
What kind of tree? What do you say? All right, last one. All right, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How is everyone doing today? Good, good. Everyone have a good weekend? I know it's too hot. I know it's been crazy hot. Yeah. On Saturday, I went to Asian American Expo with my wife and my sister and my cousins, and I have no idea how we made it through that day. It was so hot.
Wait, was that food fair?
It was in Santa Ana, and so it was like, oh, cool, cool.
Wait, how did you hear about this? I live in Santa Ana. Didn't hear about it.
Oh, I don't know. I think usually they have one in Pomona. That's the one I usually go to. I actually live closer up there, but I think they moved it down to Santa Ana this time for some reason. And so
What'd you end up eating?
we got yakisoba. It was good.
I was sampling different things. Like started with like one of those potato wheel things.
Oh yeah,
Those are good.
yeah. Everything is good when you're baking at 100 degrees.
I had these dumplings that
Yeah,
were. It was a pizza, but it was a dumpling.
Oh, interesting,
It was
interesting.
so good.
I'll try that next time.
So it was deep fried too. I was
Oh,
like,
that sounds good. All right, so hopefully everyone's staying cool. I think that's the most important thing. So stay indoors if you can, and if you have to go out, don't go to a festival with a bajillion people and when it's a bajillion degrees outside, because that was tough. But hopefully everyone's staying cool and staying safe, right? Okay, so the plan for today, today's our, this is an ANSYS week, and so today is going to be just a straight up lecture. But on Thursday, we're going to have our next ANSYS activity, so that'll be activity 2. Okay, and so I know because there's kind of a version mismatch issue, and so the computers in the lab are running 2021 ANSYS. I think most people have downloaded 2022 ANSYS on their own computers, and so I think people are having issues like saving and opening it again. So I need to look into that a bit more and find kind of a good fix for that. And I'll figure something out before Thursday so that I can give you better saving instructions. But even if you do the archive thing and you import it again later on, I think people are having issues because of the version mismatch. So I know I've been saying I'll look into it for a week now, but it's just been kind of crazy otherwise. And so but before Thursday for sure I will figure something out. So you'll have a better way to save your project from Okay, and so the plan for today is we have a little bit more strength of materials to review. And then I think, we'll probably get done with that maybe in the first 45, 50 minutes, and then we'll start talking about mesh, which is exciting stuff. All right, any questions I can answer before we get started for today? Say again? This is lecture notes. I believe it's 2, and so it's the strength of materials. Yeah. Okay. All right. So let's go ahead and get started. So, I'm not going to do everything in this lecture note. So this is kind of my generic mechanics, strength of materials notes I use for a couple other classes. And so we're going to skip a lot of the beam theory stuff at the end. And so I just want to make sure we cover kind of the concept of stress and strain, because that's kind of what's more relevant for this class. And then once we're done with that, then we can move on to meshing, which I think is more fun than this. Okay, and so I think where we last left off here, we were talking about stress and the different components of stress. AC, yes. Is it on over there? It's a little bit warmer here. Yeah, every time I'm in here, the AC is kind of on automatic. Is there a thermostat in that?
I messed with Debbie because it's too cold.
Yeah. I think the buildings have been having issues, or maybe not issues. I think they've been trying to restrict the power because it's because we're under flex alert. Yeah. And so I think what's happening is that I think the AC is on, but they're limiting it just to try to save power. And so I'm feeling a little bit toasty myself too. I've been here since 4 o'clock, so I think that's the best we can do. Yeah, don't run your AC all the time because it's a lot of power. But I think the school is aware of it because I think they're just trying to conserve power. Okay, and so the stress. Okay, and so the thing I want you to remember from stress from last time is that stress is a multi-dimensional object. Okay? Right. And so what we remember from last time is that stress, is expressed as a tensor for most materials. Okay. And a tensor quantity also basically just means that it's stored as a matrix, okay, instead of a vector. Right. And so what we have, stress is a 3x3 matrix. Okay. And so on the diagonals of the matrix, we have the compressive components, sigma x, sigma y, sigma z, z. Okay. And then, the normal components. My mind is still thinking about my previous class. And on the off diagonals, we have all the shear stress components. For the sigmas, these are the normal stress components. Taus, these are the shear stress components. And last time, we talked about the difference between normal and shearing stress. Okay. All right. And so, I'm bringing this up again because, when we talk about stress in finite element simulations, most of the time, and you can kind of recall from activity 1, we're viewing stress as just kind of one quantity, right? And so when we viewed the stress field within our plate, it only just showed one number along with the color bars, okay? But that kind of a little bit oversimplifies what the state of stress is, because stress is actually comprised of all these different components, okay? And so, later on today, we're going to talk about, what do we mean by equivalent stress? What do we mean by principal stress, and how that relates to all these different components, okay? And so, in this matrix here, of course, you can see 9 components of stress, but in reality, we actually only need 6 because these 2 are the same. These 2 are the same, and these 2 are the same. And so the quantities that I've circled in the same color, they're the same because this matrix here is symmetric. And so there's only six unique components. Okay? But even then, six is a lot, right? And so even for vector quantities like displacement or something like that, we're used to those being vectors. Those have 3 components. And so, considering that every single point within a structure has 6 unique components of stress is a lot. Okay? And in fact, it's usually too much for most people to kind of view, even with a finite element software like ANSYS. And so, how we take those 6 components and how we kind of, distill them into single stress, a single stress value that we can look at and interpret. There's a lot of math involved in that as well. Okay. And so in fact, let's go ahead and jump right to that. And so let's talk about the idea of principal values of stress and strain. Okay. All right, so just like we said up there, stress is a complex thing to look at, right? 6 components is not easy to view at any given time. And so for the sake of kind of interpreting results and kind of analyzing our data efficiently, we usually like to take those 6 components and kind of distill them into singular numbers or singular values that we can view kind of a lot more easily. And so there's various ways that we can do this. And so, there's, with 6 different components, there's multiple ways we can run that through some math to get, 1 or 2 numbers. Okay. And so the first one I want to review here is maybe a concept that you've learned in a previous class, maybe 331 or something like that. And it's this idea of principal stresses. Okay. Right. So the idea with principal stresses is that, normally, if you look at a particular point in an object, the stress state in that point is very complex. It has both normal and shearing components. Okay. But it just so happens that if you kind of change your reference point, you kind of change your point of view, then you can kind of rotate your object or rotate the reference frame into a state where you only have normal stresses. And so I'm going to do an example in 2D just because it's a lot easier to visualize in 2D, but the same concept applies in 3D as well. Okay? And so normally, if we consider just a small part in a structure, okay? So this square right here, could be just a very small particle within the structure. Okay. Normally, the state of stress here is very complex, and so we have normal components. Okay. So this might be sigma yy. Might be sigma xx. And then we have the shearing components as well. And so we might have this, like this, like this, like this. Okay, so this might be tau xy, tau yx, okay, tau xy, tau yx. Okay, and so we have a lot of different stress components that we can deal with. But you know, if we take this particle, you know, and I drew it as a square on purpose. Okay? If we take this particle and kind of rotate it a bit. I did kind of a 90-degree rotation here just to, or excuse me, a 45-degree rotation here just to exaggerate it, but it doesn't have to be 45 degrees. And in fact, you know, the degree at which you rotate depends on the stress state. Okay, but if you rotate it a certain way, you can get it so that the exact same stress state can be expressed only in terms of normal stresses. Okay. Okay. And I think, you know, people get confused when they view this figure, right? Because it looks like, you know, the figure on the left and the figure on the right are two completely different stress states. Okay. You know, the point of principal stresses and principal strains is that these represent the exact same stress statement. So, you know, they're the exact same object. Okay. The only thing is that the only thing we've done is just that we've rotated our point of view or reference frame so that the you know, the components are in kind of convenient directions. Okay. So I always think of that one I think it's a Shakespeare quote where, you know, he talks about a rose, and so no matter what you call a rose, it's still going to smell sweet and it's still going to stab your hands when when you try to grab it, you know, exactly as Shakespeare said, right? And so this is the same way, right? And so, you know, if you have an object under some stress, right, it doesn't matter what reference frame you look at it with, you know, the stress state is the same. It's just how you describe it is going to be different. And it just so happens that some descriptions are a lot more convenient than others. Okay. And so once we perform this rotation, you know, the stresses that we see here on this rotated one, these are the principal stresses. So if you're curious about how to actually solve for these, you know, by hand, it is possible. And so, you know, normally, you know, what we have here, when we say can solve for these by hand, so normally, you know, we have our stress state, and so we have our 3x3 matrix. I think everyone just got the text that, you know, we have an emergency flex alert. Okay. I think this room in particular is even warmer than normal too, because we have all the computers in here. And so all the computers are producing heat too. And so that makes this room extra stuffy compared to other rooms. Okay. So that's our normal stress tensor. Okay. And so what we can do here is that in order to find the principal stresses, what we do is we solve an eigenvalue problem. So we find the eigenvalues and the eigenvectors of this matrix. All right, so I just drew it kind of very quickly. We're not going to solve eigenvalue problems in this class, and so that's a job for ANSYS. That's why we have the computers, so ANSYS does it for you. Okay, but that's basically how you do. Okay, but so do you guys remember learning about eigenvalues in your previous math class? At least sounds familiar. So I did too. But I will say that I don't think I really understood eigenvalues until I was like 2 years into working at this job. So it's something that was still mysterious for me for a really long time. And so, and I think that's true for the majority of the human population. And so, I think a few really smart people figured out eigenvalues, and they wrote computer algorithms to compute it for us. And now we just use those algorithms, and then we're good. And thankfully, ANSYS is one of those programs that also can solve eigenvalues. But that's basically what's happening under the hood. And so when you view the principal stresses in ANSYS, what you're viewing is actually this quantity right here. All right, so that's the idea behind principal stresses. So the idea about, and so basically to obtain them, we perform a rotation, get the stress state to only normal stresses, and then that's the one that we display in our results. Okay, so that's one way to kind of distill down this complex idea of stress into just a simple number that we can view on ANSYS. Okay. Any questions on this? Okay. All right, and so that's principal stress. And so let's talk about equivalent stress. And so another name for the equivalent stress that you'll see in ANSYS as well is the von Mises stress. Okay. And so the equivalent stress is another way to kind of take this complex idea of stress and then break it down into kind of a simpler idea, or a simpler number, I should say. Okay. Right, and so it's the exact same as principal stress. We get our single value. It's just that the way that we obtain it is different. And so the equivalent stress, we actually just have a relatively simple formula. So we don't have to go through solving an eigenvalue problem to get this. We just take our 6 components and plug it into this formula here. Okay. And so the formula for the von Mises stress is given by, we take the square root, very large square root, and we take 1/2 times Inside this square bracket is going to be all the normal components of stress, since we have sigma xx minus sigma yy squared plus sigma yy minus sigma zz squared plus sigma zz minus sigma xx squared. Okay, and then we have all of the sharing components as well. Okay, and so all of this is under the square root. And so we have plus 3 times tau xy squared plus tau xz squared plus tau yz squared. So it's a rather complicated, or I'd say long formula, not that complicated. But what you can see from this is that we obtain just a single number for stress. Okay. And the idea behind this is that I think everyone here is familiar with the concept of magnitude of a vector, right? And so if you have a vector, you can find the magnitude using the distance formula. Okay. And so this is kind of the same thing. And so this is kind of the magnitude, I put magnitude in quotes, of the stress tensor. And so I think, for most engineers, the concept of magnitude is something that a lot of people understand. And so, for most people, when they're viewing the stress from their finite element simulation, they prefer to use the equivalent stress because that's kind of, exactly how it is, right? And so they see stress as kind of this multi-component entity. And so by taking its magnitude, that's kind of a simple concept that most engineers are familiar with. And it's so popular that we decided to start measuring things like failure and yield strength according to this equivalent stress. Okay, and so on Thursday when we do our activity, what I'm going to give you is I'm going to give you a part, right? And then in addition to the material of that part, I'm going to tell you at which point or at which equivalent stress the part is going to break. And so what you're going to do is that you're going to run the simulation, you're going to compute the equivalent stress, and then you're going to see if that equivalent stress exceeds, the yield strength that I give you. Okay. And so a lot of times, if you're doing failure analysis, stress analysis, and ANSYS, the one that you're going to want to look at most of the time is going to be equivalent stress, because that's going to tell you, with pretty good accuracy if the part is going to fail or not. Okay. And so that's why, for most of our activities, I'm going to ask you at the very least to show me the deformation field and also the equivalent stress field, because, that kind of shows the magnitude of the stress. All right, any questions on equivalent stress? I'm sure what you mean by Tresca.
That's someone that took Dr. Carp.
Oh, okay. I see. Yeah, so you can view the maximum shear stress as well. So because stress is so complex, if you kind of did a little bit of exploring in activity 1, you'll probably have seen that you can view a lot of different stress results. Oh, I see what you mean. And so you can view things like the maximum normal stress, the maximum shearing stress, and axis as well. And you can even view the stress in the X direction, the Y direction, and the Z direction too. So yeah, there's lots of options, but you know, the one that we're going to use the most in this class is the Fullerton stress. You know, it wasn't bothering me last class, but now that someone mentioned to keep this class, now it's starting to get to me a little bit. I'm kind of sweating up here. Okay. All right. So the last thing I want to go over in mechanics and strength of materials is stress-strain relationships. Okay. And so I think, you know, at the end of class on Thursday, we started talking about strain a little bit. Right? And we talked about how the strain inside of material is directly linked to the amount of stress that it experiences as well. And the degree of their relationship depends on what kind of material that you're looking at. And so for the simplest case, and the case that we'll be looking at a lot of in this class, is a linear relationship. And so under a linear relationship, you know, the stress and strain are related by just a straight line. Okay? And so this is probably the equation that you've known the most. And so we have stress is equal to E times epsilon. Where of course sigma here is the stress. E here is the Young's modulus. And epsilon here is the strain. Right, and so, you know, a linear relationship like this leads to a linear line. Okay, and so if we draw a stress strain curve, we have sigma on the y-axis and then strain on the x-axis, and then all we have here is a straight line where the slope of this line is E. And so just like we talked about last week, you know, when you have a linearly elastic relationship like this, that means the deformation or the strain that you see in the object is directly proportional to the amount of load that you apply. Okay. And so if you apply double the load, you'll get double the deformation, double the load, double the stress. The same thing for half and 1/3 and stuff like that. Okay. And so this type of relationship here works well in certain situations. Okay? And so, you know, luckily for us, you know, a material that we use a lot in engineering are metals. Okay, so metals are typically assumed to be linearly elastic. So if you're using something like steel or aluminum, then that metal is going to behave just like a linearly elastic material. Okay. But even for metals, this kind of linear relationship is only valid for small amounts of deformation. And so once you get to higher levels of deformation, then what you start to see is plastic deformation, which gets a bit more complicated. Okay. And so let me just write down about plastic deformation, and then I think that's all that I want to review about strength of materials, and then we can start talking about meshing. Okay. And so in ANSYS, there's actually a setting. There's actually a setting in ANSYS where you can turn on what's called large deflections. And so when you turn on the large deflection setting in ANSYS, then it'll start to account for things like plastic deformation, where the deformation, the stress-strain relationship is no longer going to be linear. Okay. And so the only thing with the large deflections, when you turn it on, it actually increases the cost of your simulation. So, for the cases that we're going to look at, that increase in cost is going to be pretty negligible, and so you probably won't even notice it. But for much larger cases, then it starts to make a difference. And so, people, it's usually a pretty real decision that people have to make if they want to turn on large deflections, or just how much complexity they want to put in their simulation relative to the cost. Okay. All right. Any questions on this stuff before we move on to meshing? Yeah.
So the only reason you wouldn't want large deflections enabled is so it's easier to run.
Exactly. Right. Yeah. Yeah. And we'll talk about cost, a lot more once we talk about meshing. But yeah, sometimes, I think for the types of simulations that we're going to run, if you turn on large deflections, it might be a difference between like waiting 10 seconds for your simulation versus waiting 15, which is pretty negligible, I think, for most people, unless you're really in a hurry. But for much larger simulations with millions and millions of elements, it could be the difference between a few hours to a few days, which is that's a lot more significant. Yeah. Okay. All right. All right. So let's go ahead and move on. And so the next thing I want to talk about here is meshing. And for this lecture, and I think we'll probably do meshing for one more lecture. We're just going to go over the basics of meshing, just enough to kind of introduce the ideas to you and to get the basic concepts down. But we'll revisit meshing later on in the semester, because there's actually quite a lot to talk about with meshing. Okay? But first, I just want to talk about just the basics, what you're looking out for, what a good mesh looks like, and what are just some of the basic settings that you can use within ANSYS. So we're shifting gears, quite a bit, and so we just finished talking about strength of materials, and so now we're going to a very heavily an FEA specific subject. Okay, so let's kind of remind ourselves what meshing is. And so meshing is the act of taking a complicated geometry and breaking it up into much simpler shapes. Okay? And so this step is necessary for FEA because, remember, the point of FEA is that we're solving differential equations on our geometry. And so, if we break our geometry into, shapes with a fixed orientation, right? So either a bunch of squares, a bunch of triangles, that makes the task just a lot more easier. Okay. Okay. And so, of course, we're not going to get into the details of how that happens, but if you are interested, I teach a course called EGME 541, which is basically graduate finite elements. And so in there, we get into the nitty gritty of how we go from a triangle to a solution to a differential equation. Right? We're not going to get into that in this class, but we do, but, even to just perform FEA as a user, you should understand, what the mesh is, how do we get a good one, and, what options you have available. Okay, and so, because of how meshing is, there's no one best way to mesh an object, and to that end, there's no perfect mesh for an object. Because the mesh that you generate is not just a function of the geometry itself. It's a function of the type of analysis that you want to run. It's a function of how much computational power that you have. It's a function of how much accuracy that you want. So there's a lot of factors that go into what a good mesh is. Okay. But with that said, even though there's no best or perfect mesh, there are meshes that are better than others. Okay. I had a math teacher in high school where he was very stingy with his compliments, but the best compliment that he would give is for him to tell you that this is better. And so I remember he would be checking my homeworks and I'd be talking to him and say, "Wow, Justin, this is better than what you did before." And he had a stamp that said, "This is better," and he would stamp my homework with it. And so this is better, in like sparkly letters. And so I still remember that to this day. Okay. All right, and so, again, meshing is a very, very rich topic. You can probably spend, maybe not a full semester, maybe like half or 3/4 semester talking about meshing, all the different shapes, all the different intricacies, and all the different nuance. And so, it goes deep. And honestly, I have a lot to say about meshing in general. But again, this is a limited class, and so, I'm just going to give you just the most important details, but just know that it goes really, really deep. Okay. And if you really want to talk to an FEA nerd, talk about meshing. He or she will have much to say about it. Okay. And so today, we're going to just start talk about, what are the characteristics of a good mesh, and so what exactly is our goal in terms of meshing. Okay, so as complicated as meshing is, actually, I think it's pretty easy to come up with a definition for what a good mesh is. Okay, and so to put it simply, a good mesh is one that is that will give you an accurate finite element solution result with as little cost as possible. Okay. And so in that definition, I've underlined accuracy and cost, and those are often kind of the two biggest trade-offs that you're going to have to make when you're making your mesh. Okay. And so let's go over what those two mean in terms of FEA and how the mesh kind of plays a role in those quantities. Okay. All right. So first, let's talk accuracy. So what do I mean by accuracy? And so the accuracy of an FEA simulation refers to how closely your simulation replicates the physical situation it's trying to replicate. Remember, the reason that we most of the time, the reason that we run a finite element simulation is to reproduce kind of a realistic situation, a physical situation in a computer, and predict the results without actually having to go out and test it. Okay, but this ability is really only useful to us if the results that we get are actually an accurate representation of reality. Okay, and so accuracy is something that you need in order to have an FEA that's actually useful. Okay. And so the thing about accuracy is that it's not a on or off kind of thing. It's not it's not something that you're accurate or not. It's actually kind of more of a sliding bar. It's more of a kind of a grayscale thing. Okay. And so generally speaking, the accuracy of your finite element simulation will go up as the size of the elements goes down. Okay. And as the size of the elements go down, the number of elements also goes up. So more elements, more accuracy. And so there's a graph that you can make for any FEA simulation. Okay. And so on the x-axis here, let's describe the number of elements. And on the y-axis here, let's describe some quantity of interest. So let's say it's the deformation or stress. Okay. The stress that we're trying to basically emulate inside the FEA simulation, right? And so, in the simulation, let's say that we have a true value of stress. And so let's say that, we ran this physical situation in reality and we measured the stress and it's, this value right here. Okay, so this dotted line right here, this is the true value of stress. So that's what you actually would observe if you ran the situation in reality. Okay. Our goal with the FEA is to get as close to this as possible. Okay. And so generally what you see is that as you add more elements, your FEA result will creep closer to this line. Right? And so for a very small number of elements, you might start very far off. But then as you decrease the element size and as you kind of increase the number of elements, you'll get closer and closer to reality. Okay? Where eventually the two lines will basically intersect. Okay? Okay. So that's generally a trend that you can expect for most simulations. Okay. Any questions on this? Right. And so another good way to think about accuracy or another good analogy is think about trying to approximate a curved line with a bunch of straight lines. Okay. And so this should kind of tell you why adding more elements will make the simulation better. So let's say that we have a graph, just X, Y. And let's say that we want to emulate this straight lines. And so let's say that we want to emulate this curve that goes like this. Okay. All right, so if we were to just use one straight line to try to emulate this, one straight line might look like this. And so we might be able to catch the endpoints, but we kind of lose all the detail in the middle. Right? So this is not that great. Okay. But the idea with adding more lines to this is that even though the lines would be straight lines, if we add more lines, we'll be able to hug this curve a lot more closely. Okay. So let me go ahead and erase this. And instead of one line, let's use 2 lines. And so with 2 lines, we might start one here. So we might go like this, that. Okay. And so you can see with 2 lines, we made a dramatic improvement on how accurately we can emulate this curve. Okay. Still not perfect, and so especially the second element there, we're still quite a bit off, but we're looking much better than before. So 2 lines do a better job than one. Right, and then you can kind of continue this example as well. And so if you add 3 lines, it's going to look even better. 4 lines, and then eventually, if you add enough lines, maybe at like 5, 6 lines here, you're basically hugging that curved line. Basically, exactly. Okay. And so for now, kind of understanding this relationship with the number of elements and the accuracy of your simulation, that's kind of an important key. And that's why in the previous activity, I had to experiment with different numbers of elements, with different element sizes, just so that you can see the difference in results. Okay. I did get questions from some people that they changed the number of elements in the simulation, but they actually didn't see much change in the result. Right. And so I think the base case for the previous activity was 5 millimeters for the element size, and then when you took that down to 2.5 millimeters, the results for stress and deformation barely changed at all. Right? And so that's not that surprising, because for such a simple case like that, you actually don't need that many elements to reach what we call convergence, and so you don't need that many elements for a good accurate result. And so we might be already somewhere in this area where if you change the number of elements, it doesn't have that much an impact on the results, because it's already as accurate as it could be. Okay? And so if you're wondering about that in the first activity, you weren't doing anything wrong. It's just that the situation was so simple already that we had already achieved almost perfect accuracy. Okay. And so element size, I think, is one of the biggest determinants of FEA accuracy, but it's not the only one. And so there are things to choose, things like element shape, element skewness, element order that also affect the accuracy. But for now, I think having this understanding of smaller elements, better accuracy, smaller elements, more elements, that's kind of enough to to get you started. All right. Any questions on this? Yeah.
So for the exercise we did, it was a pretty simple shape, and so I can see why the elements would make that big difference change in size. But for objects that have complex shapes, would it be a lot bigger difference because the shape will wrap around it better?
Yeah. Yeah. So generally, the more complexity that you add in the geometry or in the boundary conditions, the elements are going to make a much bigger impact. And you'll see. So over the next, probably in activity 3 is probably the first time that we'll see it. There are actually certain situations where it may look pretty tame, but because of how it's loaded and because of how it's fixed, you're going to get a situation where you have to kind of keep throwing a bunch of elements at it, and it's still very hard to get accuracy too. So yeah, there's a lot of exceptions. There's a lot of nuance to this, but for the activity that we're going to do next, this is kind of enough of a good understanding. Okay, so that's accuracy. And so now let's talk about cost. And in particular, what I mean is computational cost. Okay. And so computational costs, what I mean by that is the amount of time and the amount of computing resources that are required to run your simulation. And so how this relates to elements is that generally as the number of elements in your FEA goes up, the cost is also going to go up as well.
So other than time being a cost, would it be like the equipment you're using to run ANSYS on, that
Mhm.
cost would go up?
It's not that you need that you can actually, in theory, you can run any simulation on any computer. It's just that some computers are going to run it way faster than the other ones. Because at the end of the day, the only thing you really need is a computer that can add numbers and subtract and multiply numbers. And so, some computers, if you have a more powerful processor, if you have multi-cores, it's going to do those a lot faster than, than a potato, right?
So then the cost is just the time.
Yes, yeah. But the reason I put computational resources there is that people invest a lot of money in terms of getting good computers too, and so that happens as well. And I think intuitively this kind of makes sense. So the more elements that you have, the more mathematical operations the FEA has to do in order to get the result. Okay? And so, I will say for this class, you're likely never going to have, computational costs is almost never going to be an issue. And that's not due to, me giving you easy problems. It's due to the fact that, the licenses that you guys are using for, both in the lab here and on your computers are very, very limited. And so I think, and you can find this out on Thursday, you can really push it. And so the maximum number of elements that you can have with the academic version is around 52,000, around there. Okay. Last time I checked, it was around 52,000. Okay. Which sounds like a lot. And so I think, for the simulations that we were running in activity 1, I think most people were in kind of the low 1,000s or high few hundred number of elements. And so 52,000 seems like a lot. But remember, the simulation that we ran on last time was a 2D simulation. And so once you get into 3D, it becomes very easy to kind of pump up those element counts. And 52,000 in kind of the grand scheme of things is very, very little. And so, I would say it's very difficult to do anything practical with the academic license, without running into, without getting a very inaccurate result. So
we can't really do it with these big models. All the models where you can be using are going to be small.
Yeah. And that's unfortunately that's kind of the limitation, but that's kind of how they get you to buy the software too. And so, ANSYS, they're not running a charity, and so they gotta make money too, and so, that's how they get you to pay, which is, understandable. And so, but, with that said, if you were interested in pursuing this further, there are a lot of open source options for finite element softwares out there, or other computational softwares where, you can really pump up the element counts and really, run an accurate simulation. The downside to those is that you don't have kind of a nice graphical user interface like ANSYS does. Okay. And so, for this class, it's not really going to be relevant. I think the longest you'll probably wait for a simulation, like maybe like a couple minutes or something like that. And so, it's not going to get into the hours or days long simulation that FEA can do. Okay. Any questions on this? Okay. All right. And so we have these two factors. And so we have accuracy and we have cost. And so, on the one hand, to get an accurate simulation, we want to pump up the number of elements, right? More elements means more accuracy. But on the other hand, with cost, we want to try to keep the number of elements down. And so less elements, less cost. Okay? And so these two factors are in direct opposition to each other. Okay. Well, it's an unfortunate thing, not everyone can be happy. So a lot of times you're either sacrificing accuracy for cost, or you're going to wait longer for your simulation to get a more accurate result. And there's kind of no way, there's things that you can do to kind of, play along that field, but that's generally the trade-off that you're trying to make. So when you're meshing your simulation, or when you're meshing your geometries for FEA, you have to kind of ask yourself, how much accuracy do I need in order to get a useful result, and how much cost am I willing to tolerate? Okay, and so it's not an easy question that you can answer kind of right away. It's something that you kind of learn through experience, and so the more FEA that you do, more times you use it, you kind of get a better sense of this. But if you kind of keep in mind that that's kind of the trade-off that you're looking for, then it kind of helps you kind of understand these processes. Okay? And there are ways that you can actually test and see how good is your mesh compared to other meshes. And we'll get into those kind of later in the class. But if you wanted to kind of look up something in the meantime, one very common test that's used a lot is something called a mesh convergence test. All right. So I'm kind of dying up here. So I think we're going to call it here for today. And so yeah, I think this is a good stopping point, because the next thing in the meshing lecture notes is element shapes, which I don't really want to get into yet, and so because it's kind of a long topic. And so with only 5 minutes left in the class, I think it's a little bit too soon to go over that. All right, so we'll call it here. So thank you everyone for tuning in. Thank you for everyone in person. I know it was really hot today, but hopefully Thursday we'll have our AC back. Okay? So remember, Thursday is our next ANSYS activity, and so get ready for that. And then we'll go ahead and use ANSYS, and then we'll see how a lot of this stuff gets into play. Right? So thank you everyone for coming today. Thank you everyone for tuning in. Stay cool out there. Get out of the sun, get into an AC filled room if you can. Take care of yourselves, and I will see you guys on Thursday.
So, sorry to email you. I got email saying Friday.
Yeah. So I talked to Dr. No about it. You can add today, but I just want to make sure. It's not that I doubt your abilities, it's just that we just have to ask as part of the process. Are you sure you really want to do this? Because I know if you do everything and I find it out for you next semester, you can definitely graduate.
I can't do it.
Okay. Oh, I see.
So I think what I looked at was classes next semester.
Okay.
I just planned it out, and then I'll be taking one business, and I'll have to drop out.
Okay.
So I don't know how that works with the final preparation. Because I want to. I don't know if I can try to line it up. You know that?
But yeah,
Yeah.
I think you probably have to, before you apply to graduate.
I'm just gonna show a picture.
Okay.
So I have 360 hours. Now I have I'm here from 8 a.m. to 6, 7.
Okay.
So I spent a lot of time.
Okay. Okay.
I feel a lot more comfortable.
Okay. That's all I wanted to get. So you're sure that I can go ahead and approve it. Okay. And then we can get to approve it.
I have a permit.
Okay. Awesome.
So
Okay.
it will be approved tonight and go and register once it's approved.
Okay.
Okay.
Yeah. So I'll go up to my office. I'll go ahead and approve your.
Thank you so much.
And then.
Awesome. I appreciate it.
Thank you.
Have a good one.
This one won't make the class one.
You can put that in. I mean, I'm the only one that sees the Discord, so it's okay. Oh, that's true. Hey, how's it going?
I have a question for you for advising.
Yeah, sure.
So right now, like I'm enlisted for 476 with Daniel Hernandez.
Okay.
I'm also enrolled in a section with Dr. Bing's. So but I'm trying to switch to the other section with Daniel Hernandez, and I talked to the instructor, and like he's willing to add me to the class.
I see.
But then he went to talk to the department, and they told him that I'm supposed to get a permission from like the advisors.
I see. Okay.
So I'm trying to see if there's like a way to get a permission.
Okay.
To the class.
And what's the reason you're switching?
So I have I'm a senior student,
Okay.
so I have my class. My senior class starts at, from 8 a.m. to 11:15
Okay.
On Tuesdays.
Okay.
And then
The
like,
seniors at 4.
yeah, so it's today.
Okay.
And then like I have a big gap from that time to your class.
Okay.
So I'm trying to, because like this section is from 11:30 to like 2 something.
Okay. So it fits your
Yeah.
schedule. Okay.
So it'd be better for me like that way like I could get on Mondays. I'll be free like basically from morning till like 4 p.m. So I could do like I could work or do something on
Okay.
Monday. So
Okay. Yeah. So these processes are mostly gated by the instructor, and if they're willing to take you on, because at this point it's week 3, so some instructors may not, they may not want to catch people. But if he's willing to do that, then I'm okay giving up.
yeah, he told me like I talked to him like I went to his class today, and he told me like if as long as like you could get the permission, I'm willing to.
Okay. What I do need though is I know I don't
Yeah.
doubt you, but I do need kind of confirmation from his side. So if he can send an email to the advising email, just kind of confirming that, then I'm
I'm
happy
gonna
to.
text him right now and be like, so email you directly or to the
So if you do the BSME advising, that would be
Okay.
so if you can send an email just confirming it, then I'm
So one quick question, because like the drop date is today, right?
So try to get it done as soon as possible. So
Okay.
hopefully we can get that process
Okay,
done
no
today.
worries.
Our admin, hopefully he can still do stuff. I think he's aware that the deadline is today.
Mhm.
And so, hopefully they'll still be able to. But he might have gone home early, so, but he might be working from home too soon. But yeah, get it done as soon as possible. Get him, send me an email, then I can confirm that. And then we'll get through it.
Thank you so much,
Yeah.
Professor.
Mhm.